Hello, everyone. Chapter 2, we're going to be looking at elements, atoms, and the periodic table. The contents that we'll be looking in this chapter are elements, atomic theory, atomic structure, atomic nuclei, atomic mass, electron configurations, the periodic table, and some periodic trends. Okay. Okay, so elements, there are 118 elements in the periodic table. I thought this was useful or interesting information. So on the left, we have the most common elements in the crust of the Earth. So as you can see, about almost 50% of the Earth's crust is oxygen. About 30% is silicon. We've got about 8% aluminum, 5% iron, 4% calcium, sodium is about 2%, magnesium 2%, potassium 2%, titanium is a 0.5%, hydrogen about 0.1%. These numbers roughly, they're slightly different because they're from two different sources, but they roughly agree. You can see the Earth's crust, these first two columns on the left. So you can see on this visual, this pie chart visual, oxygen is 46.4%. This other source says that it's about 46.1, so that's about 46%. Silicon, 28.2, that's identical over here, etc., etc. Then looking at the two rightmost columns, this is the Earth overall. So instead of just the crust, this is going to be the core and all, if you essentially put the Earth in a blender and read everything rather than just the crust of the Earth. Iron, about 34.6% overall. Oxygen, about 29.5% overall. Magnesium, etc. So this is not something that you would need to memorize. It's just something that's kind of useful. And it's kind of useful to start a conversation about which elements are most abundant. One thing I'll point out is right away is that oxygen is a nonmetal and silicon is a semi-metal, which is not quite a metal, but not quite a non-metal. But aluminum, iron, calcium, sodium, and magnesium, they're all metals. In this next slide, we look at the elemental composition of the human body. So it would be interesting to compare the elemental composition of a body with the Earth, seeing as you might imagine that because we evolved from the Earth, we are probably going to be similar to the constituents of the crust because we evolved from the crust, right? Okay, so this is the elemental composition of a human body. So 65% oxygen, 18% carbon, about 10% hydrogen. So let's look at oxygen. So 65% oxygen, let's remind ourselves what. So it's a bit more oxygen in us than in the crust, but just as the crust was dominated by oxygen, you and I are dominated by oxygen. Let's look at calcium and hydrogen. So hydrogen is about 9.5%, calcium is 1.5%. Calcium, sorry, I think I said hydrogen was 9.5%. What was hydrogen? Here, definitely more hydrogen in us than in the crust. And which makes sense because the crust, as it formed, was hot and it would boil all the hydrogen away. Whereas you and I are not as hot as a molten crust. So that kind of makes sense. Anyway, you can look at this over and over. The essence is not to memorize it, but just to engage the topic of elements. You don't have to memorize this either, but this is an overview of the periodic table. We can see there are 118 elements. They're numbered going from left to right, top to bottom. So you've got number 1, all the way across number 2. That's the first row. Then row 2, number 3, number 4, all the way across, number 5, number 6, number 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, etc., all the way to 118. They are separated into periods. Periods go up and down. Rows go left and right, but more about that later. And we have symbols. So H is hydrogen. He is helium. So here, this periodic table gives you all the names. And notice that each element has 2 numbers associated with it. The number that increases sequentially, 1 and 2, etc. And then another number which has decimals after it. More on this later, but it's so there's basically 3 pieces of information: a symbol or a name, and then 2 numbers. But again, more on that later. Dalton's atomic theory. So John Dalton was an English natural philosopher, and at the turn of the 19th century, he proposed, based on 3 laws, the atomic theory. So his atomic theory was that atoms are the smallest indivisible pieces of matter that retain a chemical identity. So for example, if you take a piece of iron, you can grind the iron down into a smallest unit called an iron atom that will retain a piece of the identity of the iron, the larger piece of iron. 2, all atoms of an element are identical. By today's understanding, that's no longer correct, but it was correct at the time. It's not correct today because we now know there are things called isotopes, so there are flavors of element that we'll come to later. Number 3, atoms of different elements are chemically different. That's true. So hydrogen is not the same as helium, is not the same as carbon. All elements are unique. Although some are similar, they're all unique in some way. Number 4, atoms can combine in whole number integer ratios to form compounds. Yes, that's true. Number 5, chemical reactions involve the rearrangement of atoms, not a change in the atoms themselves. And that's true. So it's good to be able to jot down Dalton's atomic theory from memory. The theory was based on these observations. These are the 3 major laws of matter. So law of conservation of mass, attributed to Antoine Lavoisier. Mass is conserved, so you cannot create or destroy mass. You can only make matter with different forms, but with the same mass. Law of constant composition from Joseph Proust. That is to say that elements can combine in whole number ratios or definite proportions. Multiple proportions from John Dalton himself. You can have the same ingredients but with different ratios. So for example, you can combine nitrogen and oxygen in a 2-to-1 ratio, a 1-to-1 ratio, a 1-to-2 ratio, a 2-to-5 ratio. They're always definite ratios, but there are multiple of them. So it's a multiple of constant compositions or a multiple of definite proportions. Atomic structure. So there are several models of the atom, but essentially the models that we'll look at in these slides are going from Dalton's featureless sphere to a sphere with a feature in the middle called a nucleus. So in the early part of the 20th century, Ernest Rutherford, who was a New Zealand scientist working in England, he discovered by conducting the gold foil experiment, where he essentially shot alpha particles of a thin layer of gold foil. some of the alpha particles hit an object, and very seldomly did they do so, but when they did, they either deflected or bounced back. So clearly they hit something with high density. It was high density because it was very heavy, so a large mass, but very small, a small volume. Therefore, a large mass and a small volume is a high density. And he labeled that as the nucleus. We now know that the nucleus is a constituent of protons and neutrons. The protons were later confirmed by Rutherford to be a positively charged subatomic particle. And the neutron was subsequently discovered by James Chadwick a few decades later, and it's a neutral subatomic particle. And you can see that roughly the proton and the neutron have about the same mass. The neutron is slightly heavier, but for the most part, people say they have a mass of 1 atomic mass unit. The electron was discovered inside atoms by Joseph John Thomson. It's a negatively charged subatomic particle, and it was discovered via the cathode ray tube experiment. And essentially, atoms are objects containing electrons and protons and neutrons, so 3 subatomic particles in different ratios. And the electrons are the subatomic particle that are typically outside of the nucleus. The nucleus is where all the mass is, and its constituents are the proton and the neutron. Isotopes are flavors of elements. Isotopes are atoms of the same atomic, they have the same number of neutrons. Sorry. Isotopes are flavors of elements. Isotopes are atoms of the same element with different masses, but the same number of protons. So by definition, if you're an element of the same kind, you must have the same number of protons, but you can have different numbers of neutrons and electrons. So for example, if you take uranium here, uranium has those 2 numbers we talked about earlier. Uranium has 92 protons. It can be written as uranium-235 because it has a mass of 235, where essentially these 2 numbers are A and Z. The larger of the 2 numbers is the A number, which is the mass of the mass of the nucleus. The nucleus contains protons and neutrons, collectively called nucleons. They roughly have the same mass, 1 atomic mass unit. We know that the smaller of the 2 numbers is the atomic number Z. That's the number of protons. If it's a neutral element, it's also the number of electrons because it has to be neutral, and only the protons and electrons have a charge. So they have to be equal in number to sum to a 0 charge. To calculate the number of protons, read the atomic number. To calculate the number of electrons, read the atomic number. To calculate the number of neutrons, subtract the atomic number from the mass number, or A minus Z, and you will get the number of neutrons. You could have an isotope of uranium, for example, uranium-238. It would just have 3 additional neutrons compared to uranium-235. Here's another example of isotopes. These are 3 isotopes of hydrogen, collectively called protium, deuterium, and tritium. Protium has 1 proton and 1 electron. Deuterium is heavier because it has a neutron. So it has a mass of 2. Tritium is heavier again because it has an extra neutron, for a total mass of 3. They are all hydrogen because they all have 1 proton, here coded in red. In these 2 examples, how many of each subatomic particle does an isotope of americium-241 have? Americium is a radioactive element used in smoke alarms. Well, americium-241, we can locate it in the periodic table. We can see from the periodic table that it has 95 protons. Therefore, it must also have 95 electrons because it's a neutral element, and these numbers must always be the same in a neutral element. We're told the isotope has a total mass of 241. So that's 241 includes the neutrons and the protons. So to obtain the neutrons, we just subtract the 95 protons, and we're left with 146 neutrons. Example 2, how many of each subatomic particle does the following isotope have? We have a strontium ion, which has a total mass, we're told, of 85. Strontium from the periodic table has atomic number 38, so we know it must have 38 protons. Notice that it's got a +2 charge, therefore it's lost 2 negative electrons. So we know it's got 38 minus 2, which is 36 electrons. These numbers can be different whenever there's a charge. If you've got more protons, you have a positive charge. If you had more electrons, you would have a negative charge. Neutrons, though, we've got a mass of 85. Subtract the 38 protons from 85, and we get 47 neutrons. How to determine the atomic mass? The atomic mass is the abundance average of the masses of each isotope. This equation here says the sum of the fraction of each isotope m. So for example, what's the average atomic mass of silicon given the following information? So you have 27.97% of silicon-28. You've got 92.23, sorry, you have 92.23% of silicon-28, and we've got the exact mass of silicon-28. 4.67% of silicon-29, and we have the exact mass of silicon-29. And 3.10% of silicon-30, and we have the exact mass of silicon-30. So what's the average? Well, the average is 92.23% of the exact mass of silicon-28. Here, U just means atomic mass units, plus, because it's an average, 4.67% of the exact mass of the silicon-29 isotope, plus 3.10% of the silicon-30 isotope. We do the calculation. Notice that we are multiplying, in each case, we're multiplying two numbers, so we have to propagate fewest significant figures. So here the 92.23 is 4 significant figures. So we have our dashed line after the 4th digit, and we give 2 insignificant digits. For this central number, we have 3 significant figures as our limiting sig fig. So therefore, we have the dashed line after the 3rd digit. The final number, again, we have 3 significant figures. So we have the dashed line after the 3rd digit. But now we're going to add these 3 numbers together. So now we're propagating least decimals. Our first number has 2 decimals, second number 2 decimals, third number 3 decimals. So we ultimately have to round the addition to 2 decimals. That's why our final answer has a dashed line after the 2nd decimal. Now, when we round our final answer, we have the 5 and the 4. This is greater than the 5 alone. So we would round up, and the 8 becomes a 9, and that's our final answer. Electron configurations. So we're going to shift now away from classical ideas to quantum ideas. Quantum mechanics is needed for a modern theory of electric behavior. Essentially, we are going to, so we know what's in an atom now: electrons, protons, neutrons. We're going to ignore the protons and neutrons and just look at the electrons. But the electrons are quantum mechanical objects, and we have to think quantum mechanically. So we're going to introduce shells and subshells. The shells are going to we're going to think of those as containing valence electrons in the valence shell, and then the core shell, they contain core electrons. But both valence shells and core shells can contain subshells. So we are going to follow what's known as the Aufbau principle, or the build-up principle. And this is going to allow us to construct our elements or build them up from quantum mechanical principles. So if you follow this diagram on the left, follow the arrows, we've listed a column of 1s's, sorry, a column of s's, so 1s, 2s, 3s, 4s, a column of p's, 2p, 3p, 4p, a column of d's, 3d, 4d, 5d, a column of f's. For the most part, we're just going to have to worry in this course on S, P, and D. And as you can see from this diagram on the right, this markup of the periodic table, these letters, S, P, D, and F, these are subshells. So the S block over on the left, the D block in the middle, the P block over on the right, and then the F block, which is usually presented at the bottom over here. These are subshells. The shells are the periods. So we have shell 1 or period 1, shell 2 or period 2, shell 3 or period 3. Now, something funny happens here. You've got shell 4, but then it goes to shell 3 and then shell 4 again. But we can accept this if we follow the Aufbau principle, which will give us the right order. So starting with 1s, we cycle back round to 2s, then we cycle back round to 2p, and then 3s, we cycle back round to 3p, and then 4s, and then we cycle back round to 3d. So this picks up this unusual 4s to 3d sequence. So literally all we have to do to get knowledge of the periodic table and the filling of shells and subshells is to follow the Aufbau principle. Let's see what that gives us. This gives us a way to write electron configurations for elements. So for example, helium is this element over here. To get to it, we have 2 electrons. We know the atomic number is 2, so we know there are 2 electrons. And we would just write 1s2, meaning that we have shell 1, the s subshell, and there are 2 electrons. Beryllium has 4 electrons. It's written over here, where I'm pointing in the periodic table. So we would fill 1s2, 2s2. So the subscripts 2 plus 2 are the 4 electrons we have in beryllium. We have 2 electrons in shell 1 in subshell S. We have 2 other electrons in shell 2 in subshell S. Shell 2 is our valence shell because it's our outermost shell. So we have 2 electrons in a valence shell and 2 electrons in a core shell. Nitrogen is written 1s2, 2s2, 2p3. We have 2 shells, shell 1 and shell 2. Shell 1 has 1 subshell, which is the S subshell. Shell 2 has 2 subshells, S and P. The valence shell of nitrogen is the second shell, shell 2, and it contains 2 subshells, but 5 electrons. 2 in subshell S, 3 in subshell P. This sounds complicated, but you definitely get used to it. And the good news is the periodic table is a reminder of all of this. And I'll post a video where I will go through a lot more examples of this holding up a periodic table. So you can look at, so just to keep this particular video as short as possible, I encourage you to look at neon through xenon, locate the atomic number in the periodic table, locate it in the periodic table itself, and then read from top to left, from top left to bottom right as you go across, and follow the electron configuration according to the Aufbau diagram and this diagram. So if you have these 2 objects in front of you and the periodic table, with a little bit of trial and error, this should start to make sense. The periodic table itself is split up into regions. We have representative elements, which are main group elements of type A. We have transition elements, which are type B. So if I go back here, the representative elements are going to be the S and the P. The transition metals are going to be the D in the middle over here. We can have, amongst all of the elements, there are metals, non-metals, and metalloids, but more on that in the next slide. There are families where elements have similar characteristics, and I believe more on that. Yeah, in a couple of slides, there'll be more on that. There are group 1A and group 2A, alkali metals and alkaline earth metals. They are groups 1 and 2, so they're both in the S block. That's where you have the alkaline earth metals. The chalcogens, which you will find in group 16, which is over where oxygen is. You have the halogens, which is group 17, which is over where fluorine and chlorine are. And you have the noble gases, which is group 18, which is right at the end, which is where helium, and right at the very last group in the periodic table. Okay, you also have the inner transition metals, the lanthanides and the actinides. This is the F block, which is down here. Okay, here's another way of looking at the periodic table in terms of metals, semi-metals, and non-metals. So as you can see, the vast majority of all elements are metals. More about what a metal is later. Around 75% of all elements are metals. Around 24% of all metals are non-metals. Sorry, around 24% of all elements are non-metals. And some kind of mixture of the two extremes are the semi-metals. And they tend to border the great divide between the metals and the non-metals. But more on what distinguishes a metal from a non-metal later. There are some trends that are important to know. And broadly speaking, what we need to know are size and strength. So let's look at size first. When we say size, we mean radius of the element. So these are the representative elements, or the S and P block only. And as you can see, as you go down a group, no matter which group you go down, the elements tend to get larger. No matter which group you're in, if you go from top to bottom, they get larger. No matter what period you're in, as you go left to right across a period, the elements get smaller. So I would know this as a fact in this course. Shifting over to the right side, looking at strength, there are two ways that we can typically measure strength of an element. The first one, let's say ionization energy. This is the energy needed to remove an electron. As you can see, if we go down a group, so this is kind of tilted on its side, and we're really only going to be interested in the main groups again. So in this diagram, you can ignore the red and the green elements here. Just look at the blue and the yellow. As you go down a group, the elements get weaker. As you go down any group, they get weaker. As you go from left to right, they get stronger. Now, here's where we have to be careful. We have to treat the metals and non-metals separately. So I would consider the trends for strength as just the metals and the non-metals separately. So look at the blue region alone and the yellow region alone. So we go left to right across the blue region, it gets larger, the elements get stronger. Separately, as we go from left to right across the orangey yellow region here, the bars get higher, the elements get stronger. Going down here to electronegativity, this is a different measure of strength. Rather than removing an electron from you, so ionization energy is kind of like grip. How tightly does the element grip its electron? Electronegativity is how hard the element can pull another electron towards itself, so it's your pulling power. Same trend as for ionization energy. They tend to get weaker as you go down a group. They tend to get stronger as you go from left to right across. Notice the difference between electronegativity and ionization energy. Ionization energy includes the noble gases. Electronegativity basically doesn't include the noble gases. So for now, think about why that is. And the last slide for this video is just an overview of some trends. So this summarizes what we've just looked at. So here's a mock-up of the periodic table. So size increases down a group, the atomic radius increases down a group. The atomic radius increases right to left across periods, or you can think of it decreases left to right across periods. That's this arrow here. Metallic character, this is just you are less like a metal. And we said earlier that you are less like a metal if you're a non-metal. So this is going from bottom left over here to top right. You are becoming less and less like a metal. So that's why your metallic character decreases top left, bottom left to top right, or it increases top right to bottom left. And your strength or your ionization energy and electronegativity increase left to right across periods. And it would also increase going up a group, so bottom to top, up at any group. So this summarizes these trends, and that concludes this video.